For a quick review of Newton's method, it's used to estimate the zeros of a continuous differentiable function. We always begin with some reasonable guess, x naught. Then, using iterations of the following recursive formula, we'll quickly hone in on the actual zero. Your next guess uses the previous guess. So previous guess minus the ratio of the output of your function at your previous guess minus the derivative of your function at the previous guess. So if you want x sub 1, then you know x sub 0, x sub 1 is equal to x sub 0 minus f of x sub 0 over f prime of x sub 0. And if you want x sub 2, then you're going to use x sub 1 and the ratio of the function and derivative at x sub 1. Onward and onward. With respect to the notation, these mean the exact same thing because these subscripts on the right are always one smaller than a subscript on the left. Here it's more obvious, but they're the exact same thing, and this one is less writing, so I'm going to use this one. All right, so we could try to estimate a solution to an equation like this if we let some function equal this expression, and then we want to know when that function is equal to 0. So what are the x values which make the output 0? With this Newton's method, we need to know the derivative multiple times. So always start by clearly identifying your function and the derivative of the function. Now, since our formula is going to use the function's output and the derivative's output, we might, with the table, keep track of the function's output and the derivative's output. That way, when it comes time to use the formula, we can just use these values that we've computed and keep it nicely organized in a table. So let's start with the guess. We might think that this is about -2, so that'll be our first guess. So to find x sub 1, we're going to need to evaluate this expression for x sub 0. So we need to know f of x sub 0 and f prime of x sub 0. So our first guess, x naught, x sub 0 is -2. The function evaluated there is -9. And the derivative when x is -2 is 19. So that's our first guess. Our next guess will be the previous guess minus the function evaluated there divided by the derivative there. That's x sub 1. All right, so to get to x sub 2, we're going to need to know the function evaluated at x sub 1 and the derivative of x sub 1. So once we have those, x sub 2 is the previous value minus f at the previous value divided by f prime at the previous value. This is about -1.299. That's x sub 2. So to get to x sub 3, we're going to need to know f and f prime at f of x sub 2. So those values are. And the third guess will be the previous value, which is x sub 2, minus f of x sub 2 over f prime. Well, this is getting pretty messy, and that's why we should learn how to use our calculators to do this, because our calculators have a very nice recursive function ability built into them. So you'll want to enter your function under y1, the derivatives function under y2, because our recursive relationship uses the function and the derivatives function. So we'll have y1 divided by y2 here. And another thing we're going to be using that you might not be familiar with is down here underneath your 3 key, above the negative key in blue, A and S represents previous answer. So when you hit the second key and then this key, A and S pops up. It will always use whatever your previous answer was. So we'll be using that to do this recursive relationship. To begin this process, you take your first guess, your reasonable guess, enter it, and hit the enter button. so that it actually gets entered into the calculator, because at this point, when you use the little A and S now, down here, whatever your previous answer was, which in this case is -2, will be in the register for A and S, and we can use it in equations, which is going to be here, and there, and there. That's going to look like the following. So after entering your first guess, then type in second A and S to get answer, which is your previous answer, then minus your function, which is in y1, evaluate at your previous answer, divided by your derivative, which is in y2, evaluate at your previous answer. Hit the enter button, and you get -1.526. That's -29/19. Now to get your next guess, your calculator is ready to go. If you just hit the enter button, it's going to do the exact same thing that you did last time, using the exact same expression, but now answer is going to use this previous answer, and it's going to do exactly what we need it to do. So we'll just hit enter, and we'll get x2, we'll hit enter again and get x3, and there's no more work to do. Let's see what that looks like. We just keep hitting enter, and it keeps doing the recursive formula, and we're honing in on that 0. You can see it doesn't take very long before we are extremely accurate. We're not even changing anymore. This is only like 5 or 6 iterations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're not even changing anything up to 10 decimal places at this point. So we're very accurate after a very short number of iterations. All right, let's do another example. All right, for this final example, let's estimate the cube root of 50 two ways. First, we'll do it using differentials, and then we'll do it with Newton's method. So if we use it with differentials, we know that 64 is a perfect cube. So the cube root of 50 will be approximately equal to this cube root minus some differential in the output. So if y is a function of x, and if y is the cube root of x, then y of 64 is the cube root of 64, which is 4. Well, y of 50, or the cube root of 50, will be equal to the cube root of 64 minus some differential in that output. So 50 can be thought of as the original x value, which in this case is 64, plus some differential, which in this case is -14. So we're going to get our estimate by taking this output minus a differential in output, the estimated difference, using derivatives and differentials. So if y of x is equal to x to the 1/3, then dy dx is 1/3 times x to the -2/3. Multiplying both sides by the differential dx, we get dy is equal to 1/3 x to the -2/3 dx. All right, well, so for this scenario, our x value is 64, and our differential of x, our delta x, is -14. So our differential in y is 1/3 times the x value to the -2/3 times the differential in x, which is -14. So we can use this error in x, or this differential in x, to get a propagation of the error in y, or the differential in y. This is all equal to, well, 64 to the 1/3 power is 4. So 4 to the -2 is 1/4 to the 2nd. So 1/3 times 1/16 times -14, which is -7/24, is our differential in y. So we can now estimate the cube root of 50, because 50 is this x value plus this delta x, this differential in x. And that's going to be the output for 64 plus some differential in y that's caused by this differential in x. And finally, y of 64 is 4, and the differential is -7/24. So 4 take away 7/24 is 3 17/24, or about 3.7083. And let's see how close that was. Pretty good. That estimate of the cube root of 50 is only off by about 2/100 of a value. Not bad. All right, now let's use Newton's method. Recall that Newton's method finds zeros. So if we want to find 0, we want to find this value, you want this to be a 0. So what would that be a 0 of? It would be a 0 of the function f of x equals x cubed minus 50. Because if we cube the cube root of 50, we'll get 50, and 50 minus 50 is 0. So if you can find the zeros of this function, you will know the value of the cube root of 50. So we're going to estimate that with Newton's method. Recall that with Newton's method, we need the function and the derivative. So the derivative is pretty simple. All right, what's the recursive formula? If you have an estimate, then the next estimate will use the previous estimate minus the ratio of your function evaluated at the previous estimate divided by the derivative at your previous estimate. So we always need a first guess. What's a reasonable guess for a value of x, which will make this equal to 0? Well, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. So I think 4 is a pretty good first estimate for what the cube root of 50 is equal to in the context of Newton's method. All right, now that we have x of 0, we can find x of 1 by using this formula. So x of 1 equals x of 0 minus the ratio of the function at that previous x value divided by the derivative at that previous x value. What is that all equal to? Well, it's 4 minus, and we put a 4 in there, we get 64 minus 50, or 14. And when we put a 4 in there, we get 3 times 16, or 48. This is 7/24. 4 minus 7/24. Whoa, that's the same thing we had over here. 4 minus 7/24. Oh, wait, this is, 7/24. So we get the same thing. For our first guess anyway, but with Newton's method, that's just one guess. We're going to get closer with the next guess. Closer and closer and closer. So for the next guess, that will use our previous guess minus the ratio of f at our previous guess over f prime at our previous guess. And this is equal to, all right, at this stage, we've established that we know how to use Newton's method, but now we're going to get the calculator and use the recursive nature of the calculator. So we'll put our function x to the third minus 50 in y1, the f prime, the first derivative in y2, and then we take our guess, enter into your calculator, and hit the enter button so that it enters into that registry, because we're going to be using this button, remember, the second negative sign to get the previous answer, this little ANS, which in this case is 4 in the beginning. So then we're going to do the previous answer minus y1 at the previous answer divided by y2 at the previous answer. And it doesn't take long. There's our first estimate, our second iteration, our third iteration, our fourth iteration, and you can see we already have a very high degree of accuracy for our estimate to the cube root of 50. It's about 3.684. What exactly is the cube root of 50? Or at least, according to what our calculators say, it's in 9 or 10 decimal places. Well, here is what the calculator gives us, and as you can see, after just 5 iterations, we get the same accuracy that the calculator gives us. In fact, Newton's method is what the calculators do to generate all these answers when they give answers to the 9th or 10th decimal place. All right, well, that does it. I hope this helped you with your understanding of differentials and Newton's method.